In this lecture, I will show you two examples for exact differential equation showing method of integrating factor. So in the first example, 2xy dx plus y square minus 3x square dy equal to 0. We know that in order for the equation be exact, it has to be in this form. So first you think for a potential psi, the function of xy is a constant c. So you look for psi. So if the equation has to be exact, then it has to be in the form of partial psi partial x times dx plus partial psi times partial psi partial y times dy equals 0. Okay, where partial psi with respect to x is 2xy and partial psi with respect to y is 2 y square minus 3x square. Okay, so since you have this partial derivative, so you can check for mixed partial derivative, so which is psi with respect to y and with respect to x. Okay, so you take the derivative with respect to y, 2xy, and you get 2x. Good. Now you take the derivative of psi in the other direction, so xy. The psi sub y means partial psi with respect to y, which is this quantity. So dx of y square minus 3x square equals minus 6x. Excuse me. So you get mixed partial derivative of psi, and they are not equal. So it's good enough. It tells you that the equation is not exact, and you need to find an integrating factor. So you look for an integrating factor mu, and it could be a function of x or it could be a function of y. We don't know that, but that will be understood once we work it out. So what you do is you look for an equation for mu. So you said d mu dx equals, so you construct a fraction, and where in the denominator on the left hand side it is a d mu dx, and this dx tells you what could be here. So this dx tells you that here it could be the coefficient of dy, which is this quantity y square minus 3x square, and on the top you look for the mixed partial derivative and the mismatch. So mixed partial derivatives of psi were not equal, so you take the difference. But now you have to be careful that you have to go with yx minus xy if you are looking for mu with respect to x, and then you put here mu. So psi yx, which is 2x minus 6x divided by 3x square, and you realize that this quantity is not a function of x, because you are looking for a differential equation with respect to x, and you want to put it in the form of first order linear differential equation. So the coefficient of mu should be a function of x. You are looking for a differential equation of x and mu. Okay, so this does not work. You cancel out. Okay, so you roll out for mu to be a function of x. So you try d mu dy. And this time in the denominator you put the coefficient of dx, which is 2x. So everything is going to be reversed. So psi xy minus psi yx times mu equals 2xy in the bottom, in the top psi xy, which is negative 6x, and then minus 2x times mu. And now fantastically you see that you have minus 8x on the top and 2x on the bottom. So you can assuming x is not equal to 0, so you can cancel it, so you get negative 4 over y times mu. And the coefficient of mu, now you see that this is a function of y. So you are looking for a differential first order linear first order differential equation d mu dy equals something as a function of y times mu, and that is separable. So which means you can rewrite in this form. So see, this can be made separable in the second case. In the first case, it is impossible to make it separable because of y square minus 3x square. At this stage, you integrate to get ln of mu equals minus 4 ln of y, and we want mu and y to be positive or absolute value. We are not going to write down absolute value just for simplicity. Ln of y to the power 4, negative sign, right? So mu equals y to the power minus 4. So ln get cancelled from both sides, and this is your integrating factor, or short form, let's say IF, integrating factor. So what you do next is you take your differential equation 2xy dx plus y square minus 3x square dy equals 0. Is this what we have? Yes. And multiply this by y to the power minus 4, which is your integrating factor. And then you write this in the form d psi dx dx plus d psi dy dy, because this equation after multiplying by the integrating factor it has to be exact, and if it is exact then it can be written in the form of partial psi partial x dx plus partial psi partial y dy equals 0. So it means you can find the potential psi by writing this, which you can integrate, and the integration is with respect to x, and since it is with respect to x, y to the power minus 3 is a constant, so antiderivative of 2x is x square y to the power minus 3 and plus a constant of integration, which I'm going to write as a function of y because y is kept a constant. Now you compare this psi with this, and you see that if this is the psi and this is d psi dy, which is this, so the derivative of this quantity psi with respect to y must be equal to the coefficient of dy. So d dy x square y to the power minus 3 d dy, which is partial derivative of course, equals y to the power minus 4 times y square minus 3x square and you differentiate on the left hand side. The first term is going to be negative 3x square y to the power negative 3 plus h prime y equals multiply and you see that this quantity and this quantity get cancelled out from both sides. Y prime y h prime y equals y to the power minus 2. And now you integrate to get y to the power minus 2 with respect to y, which is minus 1 by y. Hence you have psi equals c. That is what you expect your solution. So psi is here x square y to the power negative 3 plus h, which is coming from here. So minus 1 over y equals c. And this is going to be your implicit form of the solution of the given differential equation. Good enough. I hope it is clear. If it is not clear, just replay the video to make sure you are understanding that. And I'm going to show you a second example in which I have cos of x times dx plus 1 plus 2 over y times sine of x dy equals 0. And the same way, I want to solve this differential equation. I'm told that this equation is not exact, so I want to find the integrating factor. Nevertheless, I will first start checking whether it is sure that it is exact or not exact. So as I said before, in order for the equation to be exact, it has to be d psi dx times dx plus d psi dy times dy equals 0. And you look for mixed partial derivative psi yx, which is d dy of cos of x is 0, psi sub xy, so which is just derivative of psi with respect to first y and then with respect to x. So derivative of psi with respect to x, derivative of psi with respect to y is the coefficient of dy, so which is 1 plus 2 over y times sine of x, and this equals 1 plus 2 over y cos of x. Okay, so and we can clearly see that the mixed partial derivatives are not equal. Psi sub yx is 0, psi sub xy is 1 plus 2 over y times cos x. So this quantity is not equal to that quantity, which guarantees that we need to find an integrating factor. So I'm going to look for an integrating factor. So I'm going to think that it is a function of x, because I don't know whether it will be a function of x or not. So d mu dx, so in the denominator I put 1 plus 2 over y sine of x, which is the coefficient of dy, and in the numerator I put psi yx, minus psi xy. See the order. I'm differentiating with respect to x on the left hand side, so I have to order in the other direction, yx minus xy, and psi yx is just 0 minus xy is 1 plus 2 over y cos of x, and divided by 1 plus 2 over y sine of x. And you can see that I'm missing a mu, so I'm going to put the mu here. Okay, so 1 plus 2 by y get cancelled, so you get d mu dx is just negative cos of x by sine of x times mu, and this time you have found a separable equation, first order linear, which is separable, and you are able to solve this by separable technique. So you said the mu over mu equals negative cos of x sine of x dx. Okay, so integrate it, so you get the ln of mu on the left hand side, and on the right hand side is cos of x divided by sine of x dx. Okay, so you substitute u equals sine of x, this is easy integration, du equals cos of x dx. So the integration is going to be du by u minus ln of u equals minus ln of u is sine of x, or you can write ln of 1 by sine of x. So on the left hand side, just write down for clarity ln of mu. Okay, so ln of mu equals ln of 1 by sine x, meaning that mu is 1 by sine x. So what's next? You write down your differential equation, which is cos of x dx plus 1 plus 2 over y times sine x dx equals 0. Multiply the equation by the integrating factor, so multiply by 1 over sine x, and you can see that on the second term sine x cancels, but in the first term you have something, and hope you remember now what to do, because if this equation has to be exact, and this is exact because I have multiplied by the integrating factor, so this is in exact form, so it has to be in the form d psi dy equals 0. Okay, so what's next? D psi dx is cos of x divided by sine of x. You compare, so psi is integral of cos of x by sine x, and this integration you just have solved, which is ln of sine x. Now plus a constant of integration, which is h of y. Now you differentiate psi with respect to y, which is ln of sine x plus hy, ln of sine x plus hy, which would be now h prime y, equals d psi dy. So after multiplying by the integrating factor, this quantity must be d psi dy, and here what happens is that sin x get cancelled, so you have 1 plus 2 over y. Okay. So in the left hand side, the first term is ln of sin x, differentiation with respect to y, which is 0. So 0 plus h prime y, which is 1 plus 2 over y. H of y, integrate both sides. So in the left hand side, you integrate h prime y, which is hy. So on the right hand side, you integrate 1 plus 2 over y with respect to y. So integration of 1 with respect to y is just y, plus integration of 2 by ln y. So 2 is a constant, 2 by 1, 2 by y. So integration of 1 by y is just ln of y. Okay, and I'm going to ignore the constant of integration. So I have psi equals c, which is my solution, and psi is coming from this quantity ln of x plus hy, and hy is y plus 2 ln of y. So the solution is given by ln of sin x plus hy, which is y plus 2 ln of y equals constant. And this is the solution written implicitly